Yeah, you're audible.
It's pretty clear, right?
Yeah, it sounds good.
So let's begin. Okay, so hello everyone. This is JigyasaSourtha, and today we will be discussing on the intro to the matrices. That is a part of SPC 22 session 3. So first of all, what is the matrix if it's asked? So actually you guys might have studied in your 11th or 12th about the matrices. Pretty similar to it. It is actually the arrangement of all the elements in the rows and columns, or you can say it is a way to store the elements in a form of a table. It has always two indices, the one which will be for the row and the other will be for the column. And the first index represents the number of rows and second represents the number of the columns. For example, this is an implement, or you can say just a pictorial picture representation of a matrix. So here the data type represents what the data type you will be using, either integer, float, character, or double. The list here represents the name of your matrix. Here 3 represents the number of the columns and 5 here the number, sorry, 3 is the number of the rows and 5 here represents the number of the columns, as you can see here. Now, when it comes to declaring a matrix, so if you want to declare a matrix, first of all, you always need to write a data type. Here the data type, as already mentioned, you need to represent either it is an integer, float, or character. You have to give the name to your matrix. You have to mention the number of rows and the number of the columns. As mentioned, for the number of the rows, it can either be an integer constant or it can be a literal. That is, it should be either taken as an input or it can be a constant. It cannot be a variable. It's like you have to either take its value as an input or it should be a constant. For example, I have defined a matrix here. Let's say int list, which have the number of rows as 3 and the number of columns as 3. As mentioned here, the data type that's mentioned is integer. The name is given as list. The number of rows are 3 and the number of columns are 3. And so let's say if I want to declare or I want to store a maximum and minimum temperature of a city for a week. So how am I gonna store them? Let's say if you have to store maximum and minimum temperature, the temperature can have the decimal values. For that, I'm gonna store them in the float, which will be used for storing the decimal values. You can also use the double. The name that I will be using will be the temp, which is representing the name of the matrix. The 7 represents the number of the days in a week and 2 represent the minimum and the maximum temperature. The same case if you want to store the number of employees in 9 department of 15 companies. So as you know, the data type that I will be storing in these matrices will be an integer. So I have mentioned here integer. Employment refers to the name of the matrices and 15 represents the number of the companies and the 9 the number of departments. If you go to any element of the matrix, let's say Mij, then here I will represent the number of the row and the j will represent the number of the column, where it will represent the number of the employees in the ith company in its jth department. Actually, you can also use the matrix to store the strings, as this says that you will be storing the name of 5 cities with at most 20 characters. Here it means that you will have the 5 strings and the number or the length of the strings that you can store in it will be of at most 20. So it's not a viable to use it, but still it's just a mention that you can do use it. Now let's come to the another part, that is initializing a matrix. So as we have far discussed about declaring about a matrix, let's see how will you initialize a matrix. So for initializing a matrix, let's say I have used the number of rows and the number of columns, it's a constant. I always initialize them with the help of within the curly braces. So here in the innermost curly braces, we always represent the rows. Let's say this is the row 1, row 2, row 3, and the row 4. The rows, and it starts from the column and it goes till the rows contain all the columns starting from its 0th index to the last index. You can also initialize without using the innermost braces. You can omit these braces. Even this is correct. If you want to initialize an unsized matrix, in the sense you can omit the number of the rows. It is not even necessary to use the number of the rows. You can omit it, but it is compulsory to add the number of the columns that you are going to use in a matrix. So if you're gonna ask how the compiler even know that how are we gonna consider these as the rows? So as if you mention the number of the columns here, After every second element, it will consider the next element in the next row. So this is how it interprets this list and it stores it in the matrix of the size 4 cross 2. If you want to assess the elements of the matrix, so we can say that you need to assess the elements of the matrix. So you always use the row indexes and column indexes with the indexes 2 and 1. As normal, this represents the third row and the second column element of the matrix X. Here, as usual, as you have been studying in the array, that the indices start from the 0. Same for the matrices, the indices for the rows and the columns start from the 0 and it go till row -1 and column -1. So if you want to represent the element which is present in the matrix, say X, in the third row and the second column, you will use n r -1 as the row, that is 3 - 1 2, and the column will be 2 - 1, that will be the 1. So now here I will discuss how you will input the values into the matrices. So this was the first that we have used. It was initializing a matrix. It means you know the values earlier, and this is how you initialize the matrix. But if it is asked you to take the input values into a matrix, so you will be given the two values, let's say 4 and the 2, and now you want to take the matrix input. So we are taking the input of the matrices in the row wise. That is, we always take the first row corresponding all the columns of the corresponding row, and then we go and then we ascend the row. So here the first loop here represents going through the row 1 to 4, and the columns represent going from 1 to 2, and yeah, this is how you will take the input values into the matrices. So let's come to the question. It is asked to find the diagonal sum of the diagonal elements of a matrix. So let's say you have given this matrix. As said, this is a matrix with the 4 rows and 4 columns. As mentioned, the indices will always start from the 0 and will go till column -1, and here's just for the same. As you can see, the diagonal elements or the main diagonal elements of a matrix always have their indices I and j are equal. That is, the I will be equals to the j. The indices of rows and the column will be equal. On the other case, the indices of the alternate diagonal, let's say 0, 3, 1, 2, 2, 1, and 3, 0, their sum will be equals to n - 1. As in a normal matrix, you will see their sum will be n, but as we discuss here, as the indices start from the 0, we always consider I plus j equals to n - 1. So let's say this is I am declaring a matrix of elements which will be containing all the integer elements with the name A, and the number of rows are n and the number of columns are n. Here these n are already predefined, that is, either I have taken them the input or they have been defined earlier. Here these are the two sums which I will be using to store the sum of the elements of the main diagonal and the alternate diagonal. So for the first, as we are going, so in this first loop, we are first of all traversing through the whole rows, and the second we are traversing through the respective columns of the each row. So as you can see here, we are going through the each and every element of the matrices and then checking. If I is equals to j, it means we are checking for the main diagonal element and we are storing them in the sum one. And here we are checking for if the element is an alternate diagonal, and then we are storing them in a sum. So as you guys can see, we have the time complexity for this loop running is n squared. But can we do better? So does anyone have any approach like we can do better? I think you can unmute and ask. Right in the chat. Okay, so let's say for this loop, we have been, as stated, we have I is equals to j, and we also have I plus j equals to n - 1. So what you guys can do, as you know, while taking the sum of the diagonal elements of a matrix, you guys, what are you doing? you are either checking for I equals to j and you are checking for I plus j equals to n minus 1. It means if you know the first index of the matrix, you can also know the second index of the matrix. Does that help? Okay, so let's say how we can solve this. As you can know, the diagonal elements will be having I and j equal. So if you know the first element of this matrix, let's say if you're on the first row, if your I is equals to j, your element of the matrix will be ij, that is, it will be I and j will be equal. I will be equals to j, that is, you can write I. And for checking for the alternate diagonals, instead of j, you can replace it with n minus 1 minus I. We can reduce it to the order n, that is the linear time complexity working on, where we will be traversing through each row. And while going to each row, as we know, the index of the column will be same as the row index for the diagonal elements. And for the alternate diagonal elements, the index of row will be I and the index of the column will be n minus 1 minus j. As you know, this will be the relation for the elements from I plus j equals to size minus 1. If you guys have any doubt, you can unmute and ask. I guess no one has any doubt. Okay, let's move forward. Okay, so the next question that we will be discussing on is the multiplication of the matrices. Let's say you have been given two matrices, M1 and M2, of sizes N1 cross N2 and N2 cross N3. So you have to multiply the given matrix and you will output the multiplied matrix. The given constraints, you have been given a constraint, that is the number n1, n2, and n3, the given numbers of the rows and columns of the given matrices are less than, greater than or equals to 1 and less than equals to 500. So let's say you have been given these two matrices, let's say consider it as A and B, and you need to multiply the two matrices and you need to output the matrix and you need to print the output. So how will you solve it? I guess I'm audible, right?
Yeah, you are right.
Yeah, you're audible.
Okay. Yep. Fine. Okay, so okay, let me give you a hint. Let's say if you want to find this element of the resultant matrix, that is, which will be in the row first and will be in the second column. If you want to find this element, how will you find it? You will multiply all the elements of the row 1 of the A matrix with the elements of the column 2 of the B matrix, and you will add their sum and will store them and will update in this resultant matrix. So you need to go through each and every element of this corresponding row of the eighth and the corresponding column of the B and store them here. So let's say if you want to store this element, you will be running a loop that will be running for the N2, which will be the number of the columns in the row in the matrix A and the number of rows in the matrix B. You will be multiplying the corresponding elements and you will be storing their sum. And correspondingly for each row, you will be calculating with for the each columns. So the order of the nested loop here will be 3. Let's see the approach. You have to make a nested loop of order 3. So in the outer loop, you are gonna iterate over the rows of the, let's say you are gonna iterate over the rows of the first matrix. You will create and second inner loop where you are gonna iterate over the columns of the second matrix. And for in the inner loop, you will be gonna iterate over all, let's say if these are the columns, you will iterate over all the columns of the matrices and you will store them in the M3ij, where M3 represents this matrix and I represents the ith row and J represents the jth column. So let's say for this, let's say go through the code. you have been given three integers, n1, n2, n3. You take input of the three integers. Here you declare a matrix, let's say m1, with the n1 row index and the n2 as a column index. You declare the second matrix m2. Now you take the input of the matrix m1 in the row-wise order. Here you take the input of the matrix m2 in the row-wise order. Now we have declared the output matrix, that is m3, and this is with the row n1 and the column n3. As you know, after multiplying the matrices, the resultant number of the row will be n1 and the columns index will be n3. As you need to multiply these two matrices, you need to find, you are gonna add in this element. So it is necessary to initialize the matrix. So we will be initializing each and every element of the matrices to 0. So that while adding, it will not give you any compiler error. If you don't initialize the matrix here, while just adding, it will give you some garbage value while adding it. So now if I want to take the matrix multiplication, what I am gonna do, let's say if you are going through, let's say we are gonna multiply where A represents the matrix M1 and B represents the matrix M2, and this resultant matrix represents the matrix M3. So for we are gonna first of all here I equals to 0 to I less than n1 and I plus plus. Here we are iterating over the loop. We are taking the first row of this matrix. So that means we are gonna fill the first row of the resultant matrix. When we go to the next loop, it represents we are gonna start with the first column of the first row of the matrix, or we can say jth column of the ith row of the matrix. And to fill the ith and jth element of the resultant matrix, we will be multiplying the corresponding elements. Let's say A1 with the B12 and A12 with the B22. So what we are going to do, we will be running a loop from k equals to 0 to k less than n2. That is, we will be running it over through the columns of this matrix and to the rows of the B matrix. As you know, what is the similarity here? You can see that the column or the row index here will remain unchanged from the first matrix, as it will remain the I, and the kth index, that is the number of the indices of the columns, will change. So you will represent here k and you will multiply with the matrix element of the second matrix and you will store them. So here how this loop, the innermost loop will represent adding the element, each and every element of a matrix. J's represent you are adding in the jth column, and I represent you are adding in the ith row. So if anyone has any doubts, can ask about any approach or anything else. Okay. I guess you guys won't have any doubts, so let's proceed to the next question. Okay. So here you have been given a matrix with the, okay, the question starts with the matrix search. You have been given a matrix of m into n size, and you have to search a value target. The value's name is given as target. So what are the, you have to search for a value target in the matrix of size m cross n. But the matrix has some special properties. First of all, integers in each row are sorted in the ascending order. So like when you go from left to right in any row, you will see they are sorted in the ascending order. In the same way, they are sorting in the ascending order from top to bottom when you go down below a column. And you need to find an target element in the matrix. The target element will be given. And you need to find an efficient algorithm. So what can be the naive approach for this algorithm? See, if you want to find any element in a matrix, what is the best possible way, or what you can see when you start with the naive approach, you can find at least, you can assess each and every element of the matrix and you can equate whether it is equal to the target or not. And you can find whether it is present in the matrix or not. Let's say our linear search. What we are going to make a nested loop of order 2, where we are going to iterate over the rows and the columns and will assess each and every element of the matrix and will search whether it is equal to the value or not. And here, if it is equals to the value, here the count represents a flag where I'm using it as a flag to store whether the value is present or not. If I encounter the value in any of, let's say in the ith element of the array, I'll change my flag this count to the 1 and I'll break this loop. If I break this loop, I'll move out of the loop. And let's say if after assessing any of the row, I found the element val in this loop, I'll break the loop. And when I move to the outer loop, if I have to check it again that whether I have found the element earlier row in the earlier rows or not. If it is equals to the one, it means that it has been already found in the earlier rows, then I'll break the loop. And this will, the count will, if equals to the one, will show that the element has been found, else it will be the 0 which has been initialized already. So if you go to the time complexity for this approach, it will be order of n1 into n2, as it's iterating, the outer loop will be iterating for n1 times and the inner loop will be iterating for the n2 times. But can we do better? Okay. Any ideas about can we do better for this matrix search? If you guys feel shy to speak up, you guys can also write in the chat like what you guys feel, what you think can be the approach for it, because this is the naive approach that I have been going through. I have been assessing the each and every element of the matrix and finding whether it is equal to the target or not. But if you can notice, it is matrix is not an usual matrix. It is a special matrix in which the integers in every row and the columns are sorted in their ascending order. So can you reduce the time complexity of the matrix search of the linear approach? First, we'll find the element just greater than the target in the first row. Okay, binary search can be applied, but as not everyone has studied about the binary search, yeah, we can then we'll go down the column. Okay, yeah, we'll compare with and reduce the number of the passes. Okay, see, if let's say for anyone, if anyone has been saying that you will first of all find the largest value in each row and reduce the number of the passes. Okay, who is this? Can you please unmute and speak if it's possible for you to? I guess Nathan.
Hello.
Yeah.
What I
Hi,
was
Nathan.
saying was, hello. What I was going to say was, since we know that they're in ascending, we
Yeah.
just have to start from the bottommost, let's say, row. So
You mean the last row?
sorry,
Okay.
when no, we should start from the topmost row and uh, keep going until we are able to determine that this element is going to be in this row, because we know that the largest element in a particular row is always at the end. So if we determine that the element is smaller than the last element of a row, we will know that it's in that particular row.
Okay, so like you will start from the first row,
Let's
but
say
from
we're
which
looking.
which column?
No, wait. That, mm,
Yeah, you can take your time. It's fine.
no, I don't think this will work. I'll have to think of it again.
Okay, let me help you with the given it. See, you're on a right path though, but let's say you are saying you will start from the row first. Let's say if I start from the topmost rightmost corner, let's say I start from the 15, then how will you go?
Lesser than that last element, and then keep traversing down on that last column until you reach an element which is
Okay,
greater than the
will you repeat it again? Sorry, I couldn't.
basically like whichever element that we have to search, compare it with this the last column's first element.
First row, last column.
Yeah,
Yeah.
yeah, I meant the same. And then keep
Yeah.
traversing down that column until you find an element which is greater than this element that we have to search.
Okay. And then let me say if I asked you to find an element 20, so you will start from 15, you will go down.
Yeah.
Now you've reached
Yes.
22. Now where will you
Yes.
go?
Post that, then we'll have to search in that given row.
Yeah. So like, yeah, then after 22, you will go to.
Then like start like from backwards 16, 9, 6, 3.
Yeah, exactly. That's what the approach is. Thank you for participating in it. Let's say we have been discussed the linear search. Let's say what's the idea is. Let's say I have been asked you to find 5. What I will do, I'll always start from the first row and the last column. So if you find an element, let's say your target value, the element is greater than your target value, then as you know, it is sorted in the increasing order from left to right. It means that if you go from right to left, it will be decreasing. And if from here you go to bottom, it will be increasing. So if your element present here is greater than the target, then what you will do, you will move to the next, or you will move to the earlier column. You will decrease the column number. So you will reach here 11. Let's say again, you need to find 5. Again, 11 is greater than 5. Then again, you will go to the 7. Now again, the 7 is greater than 5. So you reached 4. As you see, the 4 is less than 5. As we know that while going top to bottom, your elements will increase. As they are sorted in increasing order, will move to, you will reach 5. And this is how you found the target element 5. Let's say we need to find 20. You started from 15, you went down and you went to move to 22. But as 22 was greater than 20, you had no option other than decreasing your column index and you reached 16. You increased again and you reached 26. And after 26, it was 23, 21, and 18. But this is how you ended up here. But as you know, we cannot move any further because what we are doing, we are either moving left or we are either moving down. So this is how our loop will end. So now, will anyone want to suggest how will I write the loop values? Like this is what will be my code will be. I'll always start from the top right element that this will be. It means that from here, if I go this, the values of will decrease. And if I go from this here to the bottom, the values will increase. So if I found equals to the target, I will return the true. But if it is greater than target, I'll decrease my column index, else I'll increase my row index. But how will I end the loop? If I was just making a linear search, I will assess each and every element of the matrix. But now if as I'm not doing a search on assessing each and every element, I have to end the loop at any time, right? So at what point or what are the parameters that to be kept in mind while how the loop will break?
Like ensure that R should be always between 0 and the number of rows, and C should also be between 0 and the number of columns minus 1. Sorry.
R should be between number of.
Like zero, if number of rows are capital R and number of columns are capital C. So R should be between 0 to R minus 1, like both
Yeah.
included, and same for C, 0 to C minus 1, both included.
Yeah, that's right. So this is what. So as said, this is a code which see. Let's say you have been given two integers n and m and a target that is need to be find out. You are taking the input and you are first of all declaring a matrix here of integer, as it will be storing all the integer elements of size n cross m. So you will be running a loop from I equals to 0 to I less than n. And yeah, you are taking the input matrix here. Here, what I'm gonna do is I'm initializing the row index to be 0, as I'll be starting from the topmost row, and the column index to be m minus 1, as I'm starting from the rightmost column, that will be m minus 1. And okay, I'm using here a bool. Bool takes the represents a value false or true. So, and as found here works as a flag to just see if I found an element while searching for that element or not. So I'll always take care that my R should always be less than n, and my C should always be greater than or equals to 0. So if your matrix of, if at any point, if you find if your matrix of RC is equals to the target, you will keep your found, you will change your found, that is the flag, to true, and you will break the loop. Else, what are you gonna do? You will check if it is greater than target, you will decrease the column index. And if it is less than the target, you will increase the row index. And after this, there is the part you will check whether the found is equals to true or not. If it is true, it means you found the target value, else not. And with respect to the binary search, yeah, you can also do it in the binary search, but as it wasn't told, it will be told in the upcoming session. So yeah, you can also do it with the help of the binary search. So as our aim was to reduce the time complexity of a linear search, as it had the order of n1 into n2. What do you guys think can be the time complexity for this approach?
This one's going to be linear, right? Because we are anyways just like going off through just one or two, like one or the other. We are not going through both R and C at the same time.
Yeah, so if I want you to represent it in the terms of m and n, where n represent the number of rows and m represent the number of columns, how would you say that? Yeah, that's
Maybe
true.
like max over for
Order,
m plus n.
it will be order of m plus n. Yeah, that's true. And if you guys do it with the help of the binary search, it will either reduce to the logarithmic of order of n plus m. So yeah, it will reduce more if you do a binary search. So if you guys have any doubt in any part of the slides, you can unmute and ask, or you can either type in the chat. I guess that's all. So I'll ask the next person to take on. And then thanks to everyone. And yeah, if you do have any doubt, you guys can ask.
Yeah, if no doubts, then we can move to next part.
Yeah, hello. Are you able to hear me?
Yeah,
Fine. Okay, hello everyone. I'm Tharun Dyanish. I'm the coordinator. Today I'll be taking a session on part of the session recursion. Share my screen. You guys able to see my screen?
Yes, it's visible.
Let's start. So before going into recursion, let us get the basics of the function, because we are going to use functions in recursion. So yeah, let's get started. So why are functions required? What are they and why are they required? So functions are essentially like the blocks of the code which will be called repeatedly for multiple usage for multiple number of times. It is essentially similar to the function which we have in mathematics. So there will be an expression, and in mathematics we'll be told to evaluate for some values of x or x and y. So something similar will happen in C and C++ also, in all the programming languages. So functions can be designed to take in parameters so that the function can do different, can modify the values in the function, like it can return a different value, it can give out a different output. So for example, we can give in 2 parameters or any number of parameters. So this is an example where you can see the function gives a different output for 1, x equal to 1, y 2, and x equal to 3, y equal to 4. So, and functions can be designed to return a value. Like the output which is giving here in this function can be returned to the place where it is being called in the program, so that the value which is being returned can be stored in any other variable and can be used for further processing. And the function's job is to make if we write many functions, and the code will look organized, and it will look clean, and it will be easier to understand if anyone else is reading, anyone other than you is reading your code. Okay, so this is a basic this is a basic function. How do you write a function? So first we'll declare the return type. So void means nothing. So it need not return anything, this function. So we are going to name this function, and here we are not taking in any parameters. So the braces we are not entering anything inside the braces. And inside the function, we have the block of code which we want to execute. So now we have written this function. So how will we how will we execute this function? So we have to call the function. We have to call the function in main or any other function, so that it can be executed. So in this case, we are calling in the main function, and it will go inside the main. It will search for this function, and it will execute the code inside it. So main is the main function. So whenever we are compiling the code, it will first go to the main, and then it will start executing, and it will get all the function calls inside it and go to the function and execute it. And we can call this function from some other function also. So we can do that. So this is like even when we write a big function, if it is not being executed, we have to check if it is called or not. So I'm summarizing how to write a function here. So first we'll write a return type, which are these things. It can be an integer, character, string, bool, or void, which is nothing, and many other types. But we cannot design a function to return a whole array. So it should be it can be any of these types or some other types which we will learn after forward. And we declare the function name and then give these parameters. So inside these parameters we can inside these brackets we can give the parameters, which I'll show some examples in the next slide. And within and in this curly braces, inside the curly braces, whatever we write is the function's block. So when we call the function, this block will get executed. And if your return type is not a void, you must have a return statement, and write the variable variable or constant which you are going to return. It should be of the same type. So if you declare the return type as integer, we should return an integer from here. So let us look at some examples. This is like a very basic function where the return type of it is int. I have named it as add, and the parameters are being taken as int a and int b. So it's essentially saying that this a and b are the variables which are going to be used inside. And when we are calling the function, we call it by using add of some any two numbers. For example, I'll just show you here. So this is our function, and when we are calling it from the main function, we will use this cout. Like we are using essentially this return value to do anything. So this is like a variable. We can treat it like a variable. And we are entering 2,3, and that will be taken as the parameters of a and b and will be executed inside the code. And so another example is this one, where the return type is a character, and we take in a parameter as a string. So this return is 0. Is 0 from the strings document. We know that string can be treated as an array, and S0 will point to the first character of the string. So when we write a return S0, and when we call this function with a string inside as a parameters, it will return the first character, and we can use it for further further things. And we can also design a function to this thing to return a string. And this okay, you can figure out what this function does. This will essentially tell it will, when we give in a string consisting of many words with many spaces in between, it will return the first word, which the name itself suggests. So the naming of the functions are important, which gives an idea, basic idea of what the function does when we are calling it from the main or from anywhere else. And this is a prime function, which will when you call this function with a number, it will return if it's this prime or not. And we will not use this is like an auxiliary function. We will use this to we can use this in many places. This is a bool return type, so you can use it inside an if statement. For example, this here, you want to print out the prime factors of an integer n. What you do is that you go iterate through all the numbers less than n, and if it is a prime number and it divides n, then it has like you can output the factor. You can do much better than this code. I'm not talking about complexity here, and this is just an example of how you can use a function inside inside another function. So we let us take a close look at the parameters. We like suppose we want to define a swap function, which will essentially, like as the name suggests, we are going to swap the values of a and b. So if we write swap a comma b in the int function, it should we expect it to swap the values of a and b. But what it does is that when you're calling the swap function, this will create copies of a and b. So it will swap a and b values within this function, but it will not be reflected in the place where it is being called. So this is a wrong way to use the function, because the variables are being copied inside to the function and being used, and not the same variable which you are using to call it. You can and now, for example, you are using this array is actually a combination of many many integers or characters, so it is treated in a different way. Basically, like if you pass an array inside a function as a parameter, you have the edit access to the array which you don't have in an integer. So if you want to basically like change the array with swap the array, one of the element of an array with b, you can do this. And you have to whenever you are taking an integer as a parameter, make sure that you take the size of the array array as a parameter. Make sure you take the size of the array also as a parameter. because we would need it to stop the execution of for loops inside when you are using it. We cannot take it in implicit. The compiler does not take it in implicitly. So now I'm calling this A and B, and now I do this. I swap I input values of A and B and try swapping it and try printing it. It won't be swapped. It will be having the same values. And now I'm swapping the array with I'm taking array as a parameter. When we are inputting array as a parameter, we make sure you use braces here. It can be empty, but and when you are passing the array as a parameter, make sure you write only the name of the array. So this is the output that the A and B are not swapped, and the array's element is swapped. Array's first element is swapped. So yeah, this is how the parameters work. And now this we have done the basics of the function. Let us go into recursion. So I have told that we can call a function from main or from another function. What if we can call a function from itself? So this is an example. This is a function named print1. I'm calling print1 inside print1. What do you think will happen? Anyone?
It will keep recurring it, like it will go print hello, keep printing hello world basically.
Yeah, so this will be the output. It will be printing infinitely. Yeah, correct. And so you want to basically print only a finite number of times. So you take an integer as a parameter, and you think that you want to print 5 times hello world 5 times. So you are decrementing the parameter every time so that it you want to stop it. And we are also printing the parameter to make sure what we are doing is right. And we try to execute this now. So what do you think will happen for this? Will it stop in a finite number of steps?
No, here it won't, because you're just only decreasing it.
Yeah, we are
So
just decreasing it. So when we want to terminate a recursive function, so this is known as recursion, a function calling itself. And if you want to stop the infinite loop, you will need a case, terminating case, which is also known as the base case. So we'll see some examples of writing the base case, like some examples of base case. Before that, we'll just take a look at this meme. So don't write any recursive function without a terminating case, because that is very important. So yeah, so this is a function. So this basically this if n equal to 0 return. This return will go to the place where this function was called, and this it will not execute any code after that in the function. So basically return also even does not only return the value which is given next to it, which is corresponding to data type, it also stops the execution of the function and goes back to the place where it was called. So we are calling it as rprint10, and it will print this thing in the reverse order. So we are printing it, and we are calling the next rprint of 9. It will print 9 until it becomes 0, and it will return when it is 0 and come back. So what can we do if we want to print the numbers in 1 to 10? But using a similar function, we are using the parameter as 10. Any idea? Any idea how can we print from 1 to 10?
like keep the condition as there as long as n is less than or equal to 10.
No, you are then it will go into the same infinite case where it was there. It will go to -1, -2.
Or else keep the print n minus 1 above n. The n
Yeah,
output.
correct. So we are calling the function of n minus 1 before the output, so that it will execute rprint 2 of 9 before 10, and it will basically insert the function of whatever it does of rprint 9 inside, and then rprint 9 calls rprint 8 until rprint 0 comes. So basically when we are coming back, we go from rprint 0 to rprint 1, it prints 1, and then it comes back. When it comes back from rprint 9 here, then it prints 10. So it will be in the correct order we want, which is the ascending order. And there are and then a very classic example of recursion is finding the factorial of a number. So we all know that factorial is the product of all the numbers of from n to 1, and 0 factorial is also 1, which is a fact. And we also know that n factorial is n into n minus 1 factorial. We are using that thing here, and we return the n into n minus 1 factorial. So basically it will, when we are calling it as factorial 4, it will do factorial 3 into 4, which is the return statement here. Now it will go and evaluate factorial 3, and it will be factorial 2 into 3, and it will evaluate factorial 2, it will evaluate factorial 1 again, and when we return the value of 1 for factorial 0, it will go back throughout the ladder, and it will give you the value of factorial 4, which will be this 1 into 1 into 2 into 3 into 4, which is 24. And and another very classic example of recursion is Fibonacci numbers. And we can write the definition of Fibonacci numbers as like this, because that is a very whenever we tell recursion, Fibonacci number comes into the minds of all the programmers and everyone who knows recursion. So this is how the Fibonacci numbers are defined. I guess most of you would know this. This is also found in many places in nature. So we define Fibonacci numbers as the sum of the previous two numbers in the series, and we define when we have two base cases to take care that the function terminates. And now we want to find the Fibonacci of fifth Fibonacci number. So how will we go about it? So if you see this graph, when we are finding the Fibonacci number, fifth Fibonacci number, we will add the fourth and third numbers. And when now the function will go and evaluate the fourth number, which will be the sum of second and third, and again to go and evaluate third, which will be the sum of second and first. And now we have both second and first as base cases here, so it will return back to 4, and we also have 2. And now it will this part has been completed. It will go to the it will evaluate the third Fibonacci number, and it will be it is a sum of 2 and second and first numbers, so it will add up them both, and now we have the values of fourth and fifth third numbers. We can add up them to get the fifth. So basically this is the code which will be used for the finding the nth Fibonacci number. So like I have defined base case as 0 and 1. We can also define it as 1 and 1, which is the same, because fib of 2 will be the fib of 1 plus fib of 0, which is also 1. So this Fibonacci numbers with recursion, everyone does it with recursion. And when you try to do it without recursion, there are some methods. It's like you are just going in some random way and they're getting things done. And so, okay, we'll get into the time complexity calculations. Because we are calling multiple functions, we may wonder about the time complexity of recursive functions. So let us take some examples to find the time complexity. So we take this factorial example. What do? We call multiple functions within 4. We call one function within 4, which is 3, factorial of 3, but it will call again. So there will be so many functions called, and each function takes basically the number of time the time taken for evaluating one function is the time taken to evaluate the return statement, evaluate the whole block. And for the factorial, there is only one statement inside, which is n into factorial of n minus 1. So the time taken for evaluating the 4 factorial will be the time taken for evaluating the 3 factorial and time taken for evaluating 4, which is a constant. So it is a constant time. And we go till 2 factorial until 1 factorial, which is the base case. So what do you think is the complexity of this code? Any idea from whatever hint I gave? Yeah, it is right. It is O of n. Will
Yeah,
a for
often.
loop? Yeah. So will a for loop converted to the recursive function give the same time complexity? Yes, yes. Any like any recursive function can be written in terms of loops, and the vice versa is always true. But we prefer recursive function which makes it like condensed as a code. So, but we need to take care of the time complexity when you're using such functions. So it is so often. And now we take the example of the Fibonacci numbers. So when I was explaining, when I was telling about this graph in the previous slide, there will be, we are calculating the Fibonacci, third Fibonacci number twice. So when we are going for higher numbers, we'll have, when we are calculating Fibonacci number of sixth Fibonacci number, we'll calculate the fourth Fibonacci number here once, and also fourth Fibonacci number, which we need for to some add it to the fifth Fibonacci number to get the sixth number. So essentially, we are evaluating everything twice. So like we'll just see this as a flow chart. What will be the time complexity of this? So I'll give some example. You take the function which will give you like where you take a function. Pardon me for the bad handwriting. Take a function which adds up both if like take a function which returns the f of n minus 1 plus f of n minus 1, and you do the same and give the base case as if n equal to 1, return 1. So basically what will happen in this thing, it will go to, it will go to f of 3, and it will go till 1, and this will also do the same thing. And we know that the Fibonacci function takes lesser number of steps because one side is 4 but another side is 3. And when you evaluate the time complexity of this code, where you are splitting into 2 every time, when you do the same similar calculations as the previous factorial one, you are essentially calculating twice for everything. So time of 5 will be twice the time of calculating 4. And so basically complexity of this code will be O of 2 power n. So this will be our Fibonacci function. And also we can take another function which returns twice f of n minus 2 plus f of n minus 2. And if we do this, but we need to have 2 basic cases for this that will be taken care of. When we are just talking about the time complexity of this, we are going in the steps of 2 below. So this will basically take the time of, take O of the time complexity of this will be O of 2 power n by 2, because we are going in 2 steps below. There will be n by 2 number of calls here. So basically the time complexity of Fibonacci function lies between these both, which can be like this. I showed you this to say that this has exponential time. This has exponential time complexity. Exact calculations of time complexity will reveal that it has a time complexity of 5 power n, where 5 is the golden ratio. Most of you would be aware of it. Okay, now what can we do? So when they have asked the Fibonacci number, nth Fibonacci number, where n is even the order of even 30 or 35, then it will be it will take 2 power 30 like operations on an like in the worst case to find the this thing to find the nth Fibonacci number, which will be very large. 2 power 30 is like so huge. So when we want to find it in a time which does not exceed the time limit, we can do one thing. When we calculate fib of 3 here, we can store the same. We can use the same fib of 3 here to calculate it, so that it does not need to go through this whole tree again. So we can have an array which can be either global or can be declared inside a function and passed as a parameter. So we will use once the Fibonacci number is calculated, it will be stored inside the array so that you need not calculate it again. So this is an example of that code. We will call this as fib2 of any integer. It will go inside this function. It will form an array of length n plus 1. We are not using the zeroth element to maintain the consistency of like array of n, just as the fib of n. And now we initialize all the values to 0. Now we initialize the base cases to 1. Now we return the recursive function which where we pass the n and the array inside. So now inside this recursive, this is the main recursive function. And so if the array is not 0, which means that it has already been calculated, return it. Or if it has not been calculated, it will calculate as fib2 recursive of n minus 1 and pass the same array and n minus 2. So while calculating n minus 1, fib2 recursive of n minus 1, n minus 2 will be calculated and it will return the same function in a constant time. And you return that array into this and it will be stored inside the array here because we are declaring it here. So this will essentially take O of n time, because we are finding each Fibonacci number once, and finding a Fibonacci number is just like factorial, but just an addition instead of a multiplication. And we know the other Fibonacci number already because we are storing it inside the array. So this is how we can improvise the code, improve the time complexity of this Fibonacci, finding a Fibonacci number. And so these are some questions which we can do using recursion. We can print this pattern. So try to do this yourself. Check if given is palindrome. You know what is a palindrome, right? Which is read the same from behind and front. And now we can use it to find the sum of digits. And this is also an interesting problem, finding NCR using a recursion. And also finding maximum tariff array. You try writing this on your own recursive functions for doing these things, which will improve your skills of writing recursive function. And so now we'll go to the next part, which is GCD. So you all know what is a GCD. It is the highest common factor. And by the Euclid's algorithm, we also know that GCD of A comma B is GCD of B comma A percentage B, where we can write it. We can write A equal to BQ plus R, and find the function of find the GCD of the B and the remainder which we get. So we are using this, and we can because of this Euclid's algorithm, we can implement it recursively. And some uses of GCD are like finding the LCM and using it somewhere else using this formula. And if you after like in most of the cases, we will be using this function of underscore GCD with 2 parameters, which is an inbuilt function. You need not write define GCD function every time. So you can use this inbuilt function, which will be used most of the time when you're using for GCD. But this is a very great example of how can we use recursion for finding GCD. So this is essentially the code, which is a GCD. I'm using capital letters to not confuse with this, thing. And you have to write this as underscore GCD, where this is an inbuilt function. And now we are defining our own function GCD. And so if either of A or B becomes 0 in this A equal to BK plus R, then we can know that the other value is the HCF of the A and B, original A and B, using the Euclid's algorithm. And if for proof of for how this return statement, how this function works, if A is greater than B, you return B and the remainder of A with you get remainder of okay, I missed it here. It should be A percentage B. And if B is greater than A, you A percentage B will be A itself. And now we have swapped the positions of A and B. So we will get the higher number first, and then you can do the same thing in the next iteration. And now if if A percentage B becomes 0 in any step, we return the other value, because we can write it in terms of multiples. So yeah, there are some questions which we can do using GCD. I'll maybe do one or two, and there are some problems which you can do using recursion. Recursion basically will be useful in many other places. Like it will not be asked directly in many questions. It will be used in many further concepts. Like GCD is one example, and many other concepts too. So okay, before I do these questions, any doubt in the concept of recursion, GCD, and even functions? Okay, fine. So yeah, I guess let me do some problems. Uh, so we'll go do this one. This is an example. This is an example problem. This is an like our example problem for recursion. We can implement this question using recursion. We'll just try it out. So the problem goes as follows. What is the maximum number of squares of size 2 into 2 you can fit in a right angle isosceles triangle of base length B? And they are telling the conditions that one of the side of the square must be parallel to the base of the isosceles triangle, and base is the shortest side and it is not the hypotenuse. So yeah, I'll give you some 1 or 2 minutes to read the question, understand it, and maybe come up with some algorithm which probably uses recursion. And if you get an idea, you can unmute and tell, or maybe put into the chat. Did it get anyone get an idea of how to do this? It may not be necessary to use recursion, but this is like, since we are doing recursion, we are just trying to implement recursion in this problem. It can be done. It need not be always done using recursion. As I always said, there can be always recursion can be written in the form of loops and vice versa. Yeah, if B is 1, no square can be fitted. Fine. Okay, so how will you if I form the recursive case? Recursive step.
It'll have to start with 4. 4 will be the case where like you have one square, you can fit one square.
Even in okay, yeah, correct. So for but we need not use it here. Our recursive implementation itself will give us the output like for the corresponding things. Like we can just define a recursive function so that it will give an output of 1 for from 4 onwards, at least 1 from 4 onwards. Okay, fine. Then let me just tell the logic. So now you are having a right angle triangle of base length b, and so if even this applies for both if b is odd or b is even, now you can fit in b by 2 squares here. And we also can figure out that if the square is parallel to one side of one base, it should be parallel to the other side also. So that is a trivial thing. So now after we have inserted b by 2 squares, b by 2 minus 1, yeah, b by 2 minus 1 squares we can at most introduce, because in even case this will exceed the triangle. So we can insert b by 2 minus 1 squares in the when we start from the base, and now we have got a new triangle of length b by 2 minus 1 and of the length b by 2 minus 1, and this works for both odd and even. You can check it out. So we are going to implement, we can also always go recursively again into this. So when we are writing the code, already pre-written the code, just so that we don't waste much time. It's fine. So we are going to define, take input of the test cases. We'll take the input of the base b, and we'll return the number of squares which can be introduced inside a square of this thing b, of side b. And now I'll go to the recursive implementation of this function, which is the number of squares of b, int number of squares, int b, which is the parameter. We'll take it inside. First, we'll write the recursive step, which will return b by 2 minus 1. If I'm making a mistake anywhere, you feel free to point out. Yeah, you're right. It should be b minus 2 and it should not be b by 2 minus 1. This is basically of the length 2, right? So this should be b minus 2. And the recursive step will be, the base case will be, if n is 1, then return 0. We'll check if this works. So, yeah, this base case of 1 is not sufficient. So what Abhinav has done is better. It is like the correct implementation. We need to take care that we have the base case defined for all the cases. And since we are going the steps of b minus 2, for all odd numbers will reach at 1, and all even numbers will reach to 2 or 0. And we know that inside 0 we cannot enter any square, or for 2 also we cannot enter any square because half of the square will be lying outside. So we can write either of the cases of 0 or 2 inside, and we can now run it. So when we are calling the function recursively, take care of how many steps we are going, and then you can take, yeah. So the output is for the sample case is fine. I'm just submitting this to make sure that this is correct. So yeah, so make sure when you're defining the base case, when you are defining the base case, you have covered all the cases. So this is one thing. You can try out these things in. Okay, maybe we'll do one of these. So this is the function. If you have pen and paper, try try finding out what will this function fun with this following call output. Try doing it. Don't do using like don't code it and just compile it. Try using the logic or using a pen and paper and find out what it will output. I'll give you some time. One second, 1 minute, I'll be back. You just think about. Okay, so it seems that we are running out of time. So you can this will be in the slide. You can you do the recursion questions in GCD using using this link. You can try it out after the session. So this is just a recap that functions can be are written for repeated usage, can be parameterized and return a value. And the recursion is function calling itself. Don't forget the base case, which is usually written at the start of the function, and make sure you get the recursive call right. And take care of the time complexity when using, for example, Fibonacci function takes an exponential time. And for GCD, you can implement it recursively, or you can also do using the inbuilt function. Okay. Okay, so thank you in a very cringe way, but it's fine. Thank you for listening till the this part of the thing. So the now the next person will take care of we can take over. Like he will explain the binary search part.
Hello everyone, I'm Rishabh, coordinator of Programming Club, and before we begin our discussion about binary search, we'll have a short 5 minutes break. Meanwhile, if anyone has any doubts about GCD or recursion or functions or matrices, feel free to ask during the break. We will start.
Tharun, you are sharing your screen.
Yeah, Tharun, can you stop sharing your screen?
Yeah.
Okay, yeah, I forgot to stop sharing.
Yeah, okay, now it's fine. So we'll start at 3:50. Meanwhile, if anyone has any doubt, then feel free to ask. Okay, so before we begin, can someone confirm if I'm audible and my screen is visible?
Yes, Rishabh, you're audible. Screen is visible.
Yeah, okay. So we'll begin with binary search and let's talk about binary search now. Binary search is one of the most popular problem solving techniques in competitive programming. There are a lot of problems which can be solved using binary search algorithm. But before we talk about binary search, let's discuss about linear search or searching for an element in an array in general. So suppose we have an array made up of n elements, say a1, a2 up to an, which are sorted in non-decreasing order. And we are looking for a target value, suppose x. In case of linear search, we iterate over all the elements of the array from left to right or from 0 index to n minus 1 index. And we break out of the loop or break out of the iteration when we find the target element. So as you can see in the GIF here, our target element is 33 and we start from 10. We go on up till 33 and then we break out of the loop when we reach this element 33. So as we have covered time complexity in session 2, it can be seen that the time complexity of linear search algorithm is big O of n. And for large values of n, this is not a good time complexity. Like searching for an element will take a lot of time given sufficiently large value of n. And since we are taking a sorted array here, then we should make use of that property of the array. So we can do better. And that better implementation of searching is binary search. So suppose we consider the middle element of the array, say a mid, then there can be three possibilities. First possibility is a mid is equal to our target value x. In this case, we are done. We can break out of the loop. If a mid is less than x, then in this case, our target value lies to the right of a mid. As it's sorted in non-decreasing order, then our target value will be on the right of the middle element. So like more formally, for all indices j less than equal to mid, aj is less than x. So we discard the elements which are to the left of a mid and continue the same process of looking through the half of the remaining array. Similarly, if a mid is greater than x, then x lies to the left of a mid, and we discard the elements which are to the right of a mid and continue the same process. Eventually, we will be left with a single element, which might be x. In case x is not present in the array, then we like terminate our process and mention that x is not present in the array. So this algorithm is binary search algorithm. As it can be seen here in this GIF, we have this sorted array and mid value is first 4. Our target is 5. 4 less than 5, so we search over here. Then we get another mid 7, which is greater than 5. We search over these two. We get our mid 5, and that's the target value. Since we are basically cutting down the array in halves in each step, we will be done in log base 2n steps, like mostly. Like consider the big O notation. The time complexity of binary search algorithm is big O of log n. You can see that binary search is better than linear search, but do not forget that binary search has to be applied for sorted arrays. So this is the essence of binary search. We're breaking the arrays into two. So in binary search, there are different ways of finding the middle value. First one is like we take the 2 pointers, like as shown here, start and end. I've typed them as low and high over here. So mid equal to high plus low by 2 and mid equal to low plus high minus low by 2. So what's the basic difference between the two ways of finding mid? Can anyone unmute and speak up? Anyone can even guess, it will be fine. Okay, wait, never mind. So usually we prefer the calculating mid on the way it's shown on the right, low plus high minus low by 2. Because if both high and low are sufficiently large, like high plus low high and low both are separately sufficiently large, then this high plus low operation can result in int overflow error. That's why we prefer this way of finding the mid value. So keep this in mind whenever we implement binary search. And let's go and go over some applications of binary search, like how it is exactly used to solve problems. So consider this paradigm of solving a problem, finding closest element of a target value in an array. In a sorted array, we need to find the element closest to the target value x. I mean, formally, ai minus x should be minimum. This problem can be solved using binary search. We need to solve two separate subtasks. Find the maximum element less than or equal to x, that is closest to x on the left. Find the minimum element greater than x, that is closest to x on the right. And we choose the final answers from these two options. Here we will use 2 pointers, right R and left L. We can find mid in a similar manner. And if A mid is less than equal to x, then L equal to M and we continue. If A mid is greater than x, then R equal to M and we continue. Note that the algorithm runs till the pointers converge. That is till the time they are adjacent. That is R equal to L plus 1. During that time, our algorithm will continue to work. So as shown here, this is the array we have. Our target value is 20. So 20 lies somewhere over here between 18 and 25. So we initially keep L equal to 0 and R equal to what's this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So first our mid element is this 13, and since it's less than 20, our left moves over 13. We calculate the new mid value, which is 25. Since this is greater than 20, our right moves to 25, and yeah, our right moves to 25, and we get our new mid as 18. Since this is less than 20 as well, our left moves to 18, and since here r equal to L plus 1, we can terminate our loop and then find the minimum out of these two. So this is demonstrated here. We get the array and target value x, and left L equal to 0, R equal to n, the size of array, and initially we keep mid as 0. So our first case will be if target value is less than this first element itself, then the closest possible value can be this first element. Like suppose our target value is 1. Then in this case, the closest element will be 3, as we can't go any higher than 5 and 3 and keep it as closest element to the target. Similarly, if our target value is like greater than equal to the last element 31, say our target value is 32, then we can't go below 31 and keep it as the closest element. Otherwise, if our target value is between these two values, then we'll use this binary search algorithm. If we get the value, like suppose our target value is 18 and we get it over here, then we can break out of the loop because the closest element will be the element itself. Otherwise, we can like as demonstrated over here, as target is 20, we can keep on implementing till r minus L is greater than 1. And as soon as it's 1, we get two adjacent elements and compare those two to get the final index as the answer. So is this clear? You can type in the chat as well if you have any doubts. All right, I'll take it as it's clear and we'll proceed. There is another method of implementing binary search for solving problems. That's binary search for the answer. Usually the problems which involve a Boolean function or numbers, say from 1 to n, can be solved using binary search. Suppose we have a Boolean function f of x. What a Boolean function is that given an input, there are some conditions in the function and it gives an output of true or false based on the input and the condition. So usually we want to find the maximum or minimum value of x such that f of x is true. Note that binary search should be used to find the maximum or minimum value of x such that f of x is true. Otherwise, we can use if f of x is monotonic. So binary search can be used to find the answer if f of x is monotonic. What it means is that suppose we have some numbers from 1 to 14. So I can have a Boolean function f of x such that x is less than 9. So it is true for all numbers from 1 to 8, both inclusive, and false from all numbers from 9 to 14, both inclusive as well. So this is an example of a Boolean function. Another example is f of x is greater than 6. In this case, it is false for all numbers from 1 to 6 and true for all numbers greater than 6. These two are examples of the functions we are talking about. So we can discuss a problem which is available on lead code as well, arranging coins. I believe the problem statement is visible. I can read the problem statement once. Like, you have n coins and you want to build a staircase with these coins. The staircase consists of k rows where the ith row has exactly I coins. The last row of the staircase may be incomplete. So given the integer n, return the number of complete rows of the staircase you will build. And we have this range of n as well. So this is the required thing that we are targeting. Like, suppose we have n equal to 8, then we get 3 complete rows and the 4th row is incomplete. So does anyone have any ideas how to approach this problem and solve this? There are 2 common ways to solve this problem, so any one will be fine. You can type it in the chat as well if you have any ideas about solving this problem. Anyone?
Basically, like whichever row it should be, this summation formula you have to apply and should be less than or equal to n.
Yeah, that's right. So that's the idea of solving the problem. So like as I said, there are 2 common ways of solving this problem. We can either do this by math, like solving the quadratic equation. Like suppose there are k complete rows, then k, like summation from 1 to k, which is k into k plus 1 by 2 will be less than or equal to n, and solve the quadratic. But we can, like, we are interested in the binary search solution. So like for the binary search solution as well, let k be the number of complete rows. Then we get a monotonic Boolean function and we want the maximum value of k such that f of k is true. Like somewhat like this. It is true for all numbers less than k and false for all numbers greater than k. And this is the target value we want from binary search. So how to solve this problem? So note that our Boolean function is of the form f of x is x star x plus 1 by 2 less than or equal to n. That is, summation from 1 to x is less than or equal to n. And it is easy to observe that if this function is true for a value x, then it is definitely true for a value less than x, say x minus 1 as well. And since in the range of n we had n greater than or equal to 1, then we can keep the left pointer, the lower pointer as 1 initially. And note that in this sort of questions, we try to end up with our indices in the adjacent form. Like f of L is true and f of R is false and R equal to L plus 1. Since index R is for the value such that f of R is false, we need to start with a sufficiently large R. Otherwise, our algorithm won't work if f of R is also true at some point or initially as well. So we keep R equal to n plus 1 and you can plug in and find out that for all values in the range, f of n plus 1 is always false. So this is the solution. We take the input L equal to 1 initially, R equal to n plus 1, mid value equal to 0. And while R minus L greater than 1, that is while they are not adjacent, we calculate the mid in the manner I had demonstrated earlier. And this is our f of mid. So while it is true, we get we assign L equal to mid, otherwise R equal to mid, because it will be false and we need f of R to be false. And in our final solution will be L as demonstrated, that L and R should be the adjacent values and we need the maximum possible value for which f of k is true. So like as I have explained verbally, this is what's written. If f of mid is true, then we assign L equal to mid and continue. Else if it is false, then we assign R equal to mid and continue. And eventually we end up with f of L equal to 1, f of R equal to 0, and R equal to L plus 1. And this is where our while loop ends. Since R equal to L plus 1 and f of R equal to 0, we can be certain that L is the required answer. So does anyone have any doubts in this solution? If you have any doubts, feel free to type in the chat as well. Okay, I'll take that as it's clear and we'll proceed. All right, so another illustration of using binary search. Is the problem statement clear? Like, is it visible? Can someone confirm?
Yeah, it's visible.
Yeah, okay. I'll give 2 minutes for reading the problem statement and then we'll discuss the solution. Okay, I guess that is sufficient time for reading the problem statement. And since we have a shortage of time as well, we'll just discuss the essence of the problem statement. So Vasya, I don't know, it's a Russian name. I don't know if I'm pronouncing it correctly, but Vasya brought N candies and he eats the same number of candies, like some K candies every day. And after him, Petya eats the 10% of the remaining candies. We need to find the minimal number K such that when the candies, like when the candies are, when they have eaten all the candies, Vasya eats at least 50% of the candies. Like as illustrated in the problem statement, suppose he initially had 68 candies. Then if he eats 3 candies every day, then by the time the candies finish, Vasya would have eaten 39 candies, which is obviously more than 34. And while Petya would have eaten 29. So that's what we want. So here our Boolean function f of k is Vasya eats at least 50% of the candies given that he eats k candies every day. And if f of x is true, then f of y, where y will be greater than or equal to x, is also true. So we end up with a monotonic function like the one shown here. And like for given value, if it's true, then it's true for all the values greater than the given value. And we need to find the least value such that our function is true. So again, we'll try to get our pointers in the adjacent form, r equal to L plus 1. And in this case, f of r should be true and f of L should be false. So this is the solution. We get the input. Okay, so this is our main function. We get the input over here. We get our we specify the L value as 0 and R as N and mid value as 0. And while they are not adjacent, we calculate the mid value as demonstrated earlier. And here we need to define a checker function. Like it for our f of x is not trivial in this case. It cannot be contained in one expression itself. So I'm defining another function over here. And as Tharun explained about defining functions, I'll consider a Boolean function which has two inputs, the number of candies and the number, like the mid value. So I'm assigning another temporary variable as the number of candies and the number of candies that Vasya eats as count. So while the number of candies is not equal to 0, we will count the number of candies that Vasya eats and we'll subtract the number of candies he eats from the remaining candies, and then Petya eats the 10% of the remaining candies as well. So this is what this command explains. And then we get our Boolean function. So if the number of candies that Vasya eats is greater than the ceiling of temp by 2, then we'll return true, else we'll return false. So our final, so if it's true, then R will be the mid value and then we'll continue the loop. Otherwise, if it's false, then L will be the mid value and we'll continue the loop. As shown over here. Because we need f of L to be false, f of R to be true, and R equal to L plus 1, the adjacent form. So that's why we'll keep these two as the conditions over here. So is the solution clear to everyone? Are there any doubts? Feel free to ask the doubts or unmute yourself or ask, or type your doubts in the chat and we'll discuss those doubts. Also, guys, we have a shortage of time as well, so it would be better if you're quick to ask doubts. Okay, I'll just assume that the solution is clear to everyone and we'll proceed. So let's discuss some built-in functions in C++ which are based on binary search. There's a binary search function built in C++, but it is a Boolean function and returns true if the element is in the array between the first and last, or the L and R pointer, else it returns false. So we can use this function as, suppose, Boolean value equal to binary search A plus L, A plus R, and the target value X, where A is the array of n elements that we have. And note that this A plus R term is not included in the search range. So our X value, if it's between A plus L and A plus R, where A plus R is not included, then we'll get true, otherwise we get false. Then we have another function which is lower bound, and it searches for the pointer to the element which is greater than or equal to the target value. And the element should be in the first and last range, where last is excluded from the search range. So we can use this function to find the index of such an element, like lower bound A plus L, A plus R, X minus A, where A is the array of n elements we have. This is a part of pointer arithmetic, and like you guys can go over it if you want. The slides will be available after our session. And similarly, as we have lower bound, we have upper bound, which returns pointer to the element which is strictly greater than the target. Note that lower bound returns the pointer to the element which is greater than or equal to the target, while upper bound returns pointer which is strictly greater than the target. And again, we don't include the last, like the A plus R element in our search range. Upper bound can be used in a similar manner. Int index equal to upper bound A plus L, A plus R, X minus A. So that's it. And we have some notes about lower bound and upper bound. If all elements in the range first and last are less than the target value, so upper bound and lower bound don't work in this scenario, and the function returns the last pointer, this last one, like A plus R. So if we plug in those values, the index we get is R. And for usually the functions are used to search within the entire array. So we use these functions as int index equal to lower bound of a plus n target minus a. Again, a plus n won't be included. So if we somehow get index equal to n, then the required element is not within the array. So clearly the index n is out of the bounds for an array with n elements. So that's what we end up with. And as discussed earlier, we can use binary search recursively, like Tharun covered recursion today, and we can use binary search in a similar manner. We can define a function and use that function to implement recursive binary search. For example, let's define a function binary search int left, int right, which are our pointers, the two extreme pointers, int target value, that's the input, and int array, which is in a sorted manner. So the entire process of implementation of binary search is similar. However, instead of changing left and right indices, we modify the recursive function call accordingly. So suppose we have this binary search function, int left, int right, int target, and int array. So if left is less than the right pointer, then middle value will be calculated as in the manner demonstrated earlier. And if it's equal to target, we'll just return this index. Otherwise, if it's greater than the target, then we'll modify the right index as L, mid, and target. We are basically cutting down the array from the original R to the mid R position and keeping the L, the left pointer, unchanged. And else if A of mid is less than target, then we modify the L pointer accordingly. And because we are supposed to contain the L within our binary search function, we'll plug in mid plus 1 and leave R unchanged. And if this is not the case, sorry, if L is greater than R or if L is equal to R, then we just return -1, that the target value is not in the array. So this is the main function implemented accordingly. We get the input of the, we get the number of elements in the array over here. Then we get the elements of the array over here, and we're just assuming it's in sorted manner. If not, we can sort it. Then we get the target value, and then we get, like, I define int position. Pos is a position variable, and if it's not equal to -1, that is, if the target value is in the array, then we can just print out that we found it at position. Otherwise, we can just print that target is not in array. So can we be more efficient than binary search? Like, why can't we divide the array in more than 2 parts? Is there any binary search 2 or something? So we do have an algorithm called ternary search, where we calculate 2 mid values and look for target based upon the 2 mid values. But since we're running out of time and it's not in the scope to discuss ternary search over here, we'll just skip it. And that's a wrap of today's session. We can just review what we covered over binary search. A couple of searching algorithms: binary search, linear search. Linear search must be clear already. And then we discuss why binary search is better. The time complexity is less. It's big O of log n. And applications of binary search in solving problems. For CP, we discussed that lead code arranging points problem and the Vasya and Petya candies problem. And the built-in C++ functions, lower bound, upper bound, binary search. Then looking at using binary search recursively, and just the term ternary search. So that's all, and thank you for your attention. Are there any doubts about binary search or the applications of binary search? Okay, I think there were some doubts in the chat and I missed it. Sorry about that. For int, I'm sorry. For int, we first sort array, then use binary search. But what we do to check if a string is in an array or not? Yeah, so like as int values are sorted, and as Tanmay says that we can sort it according to, like, string values are also sorted according to lexicographical order, I'm supposed, but I don't know what it's pointed out here. Yeah, so as Saptarshi pointed out, we can sort an array of strings in the same way as we sort an array of integers. Like, thank you, Saptarshi, for clarifying it while I was busy in the session. I'm sorry about it, since we're running out of time as well. If there are any doubts, then please be quick in asking those doubts.
Yeah, no issue. Okay, so thank you, Rishabh, and thank you all who took this session, and thank you all of you also for attending till here and listening to the session, and hope you enjoyed the session. We'll release the problem set for these corresponding topics by at today evening or at max tomorrow. And like hope you enjoy the solving the problems. And if you have any doubt, you can feel free to refer to the slides and the recording. And like even if you have doubt after that, you can like feel free to ask them in the groups. Okay. We are up for taking up any doubts. If no doubts, the session is over for us from our side. Thank you for joining.
I would just like to add that since we had to rush through the binary search portion,